cs407 Numerical Analysis, Section 3.3, the Secant Method. We're now going to take a look at a general purpose procedure that converges almost as fast as Newton's method, and that's called the Secant Method. So let's begin by taking a look at Newton's method. And you'll recall from last lecture that Newton's iteration defines xn plus 1 in terms of xn, using the formula xn plus 1 is equal to xn minus f of xn divided by the derivative of f taken at the point xn. And since we can define a derivative, you'll remember this back from one of the first labs, by f prime is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And for a small h, we can replace f prime of x with f prime of x is approximately f of x plus h minus f of x divided by h. Using that formula, then what we can do is we can combine that with Newton's method. So in particular, if x is equal to x sub n and h is xn minus 1 minus xn, then we can get the following formula for f prime at xn. The name of this method is taken from the fact that the right member of this first equation is the slope of the secant line of the graph of f. Of course, the left number here, the derivative, is the slope of the tangent line to the graph of f. When we combine this with Newton's method, we get something known as the secant method, and we can define x of xn plus 1 is equal to xn minus xn minus 1 over f of xn minus f of xn minus 1, all multiplied by f of xn. Like Newton's method, we can use the secant method to solve systems of equations as well. A few remarks about this are in order. Clearly, xn plus 1 depends on the two previous elements instead of just one. So to start, we need 2 points, x0 and x1. You have to provide 2 instead of 1. The secant method can then generate x2, x3, etc. So when you're programming this, we can calculate and test the quantity f of xn minus f of xn minus 1. If that's 0, then we can get an overflow, and so we want to test that and make sure that it doesn't get too close to 0 to prevent that overflow. And if the method is succeeding, the points xn will be approaching the 0 of f. So f of xn will be converging to 0. And what you can see here in the picture is you can see the secant line. And that will begin getting closer and closer to the actual root. So again, works fairly close to what Newton's method has been doing for us. A couple more assumptions. We're going to assume that f is a continuous function. If f is not continuous, if it's poorly behaved, all bets are off. And we also would like to say that f of xn minus 1 will be converging to 0, and f of xn minus f of xn minus 1 will also be converging to 0. If those two have the same sign, then we're going to lose some additional digits in subtraction. And we want to eventually cut off the iterations when we get to some point that's less than delta, say 1/2 times the absolute value of the function, say delta is 1/2 times 10 to the minus 6th. Let's take a look at the code for this. So here is a pseudocode for using a max of n-max steps of the secant method applied to the function f. And we're going to start in the interval AB, and that AB interval is going to be x0 and x1. So the values AB here are x0 and x1. F is, of course, the external function, which you'll have to write in max as maximum number of steps, and epsilon is a bound for us. One thing to note here, we have a couple long arrows. What those long arrows mean is it means an interchange of values. So this is a swap value routine like the one that you learned in CS150. So it's going to actually take more than one step. Temp is equal to A is equal to B is equal to temp. And notice that we're interchanging the endpoints A and B if necessary to keep f of A less than f of B. So consequently, the absolute values of the function are non-increasing. So we have f of xn is greater than f of xn plus 1 for n greater than or equal to 1. And again, here's the code. We will most likely code this up during lab, but let's take a look at an example of how this works. So consider the secant method being used on p of x is equal to x to the fifth plus x to the third plus 3, with x0 is equal to minus 1 and x1 is equal to 1. We want to know what is x8. Well, we have x0. That's obvious. It's given to us. It's minus 1. And when we put in minus 1 into that equation, we get minus 1 plus 3. So p of x0 is 1. Do the same thing with x1. It's 1. And when we put in 1 into the p of x equation, we get 1 plus 3. It's 5. Now, x2 is defined by the secant. X, which is going to be x1 minus x0, f of x1 minus f of x0 times f of x1. That's 1 minus 1 over 5 minus 1, so that's 2 over 4, which is 1/2 times 5. That's 1 minus 5 halves, which is minus 3 halves, which is about minus 1/2. And when we plug minus 1/2 back into the p of x equation, we get about minus 7.97 with the calculator. So that's how to do the first 3 steps by hand. Let's run it out on the computer, and this is the result that the textbook derived. So these are the results of running the secant method to x8. If you use the mathematical software to find the single real root, you'll get minus 1.1053, and it'll also give you 2 pairs of complex roots. Let's take a look at the convergence analysis and errors for this method. So, a couple advantages to the secant method are: 1, after the first step, only 1 function evaluation is required per step. That's in contrast to Newton's method, which requires 2, and it's almost as rapidly convergent as Newton's method. In terms of convergence, it can be shown that the basic secant method obeys an equation of this form here. I'm not going to read the entire thing out for you, but a couple things to know in terms of these letters. This one here is our good friend xi that we introduced earlier, and this one is zeta. So it obeys this form of the form, and it says basically that's going to be how quickly we converge. So this is somewhere, in terms of actual performance of convergence, it's somewhere in between bisection and Newton's method. A little faster than bisection, a little slower than Newton's. And if you're actually interested in the mathematical proof, you can find it on pages 144 to 145. And in keeping with the spirit of good math books everywhere, the authors leave part of it as an exercise for chapter 4. If you're, quote, the interested reader, you're likely going to be invited to prove that. Currently, I have too many invitations in terms of my social life to take them up on that. But perhaps at some other juncture, I would deeply enjoy taking them up on that invitation. So the order of convergence for the secant method can be expressed in terms of this inequality. The error term, n plus 1 error term, is less than some constant c times the nth error term raised to the alpha power. And alpha here is 1/2 times 1 plus the square root of 5. Now that's greater than 1, so we say the convergence is superlinear. And the error approximation is going to be the absolute value of the error term is equal to c, our constant, times e sub n raised to the alpha. Now, looking at that alpha, you may recognize that as a special number. Namely, 1/2 times 1 plus the square root of 5 is properly known as phi, or the golden ratio. Now, if you took CS 151, you may remember that we used that in the lab once upon a time, and that phi and its complement can be put together to form Benet's formula. You can also use it in the Fibonacci numbers as part of the two proofs of this convergence found on page 146 and 147 of the text. Assuming that the inequality is true, we can then show the secant method converges under certain conditions. So that pretty much rounds out the secant method. Let's take a look at the comparison between the different methods we explored in Chapter 3. So in this chapter we looked at three primary methods for solving an equation of the form f of x is equal to 0, and the first of these was the bisection method. Now, it's reliable, pretty easy to code as you found out, but it is a bit slow, and you also have to provide 2 points where the function takes on opposite signs. And the function also needs to be continuous, but most of our functions need to be well behaved. Newton's method, that was one we looked at in 3.2, very fast, but often only near the root, and you can get runaways and things that go off to infinity if you're not careful where you start at. You also need to program the derivative f prime of x. So, using Newton's method, you need to specify a starting point near the root, and you need to have a differentiable function. It can be interpreted as the repetition of a two-step procedure summarized by linearize, and solve. And we're going to use that strategy quite a bit, so it's important to know how Newton's method works. And it's a handy tool, this linearize and solve approach, and we're going to see that time and time again, much like our friends the Taylor series. Finally, the secant method, it's nearly as fast as Newton's method, and you don't need to have the knowledge of the derivative. It may or may not be available, or it may be too expensive to compute, so this is good for avoiding the calculation of the derivative. It does require us to have 2 good starting points, and it's often faster at approximating roots of nonlinear functions in comparison to bisection and false position. One thing to note is the slope of the secant line can be quite small, and the step can move far away from the current point. The secant method can fail to find a root for a nonlinear function that has a really small slope near the root, because the secant line can jump quite a bit. So, for nice functions, those are our well-behaved functions, continuous functions that don't have jumps and things, and guesses relatively close to the root. Most of the time these are going to work out with relatively few iterations, usually 3 to 4 sometimes. In the case of Newton's method, it's going to give us a really good approximation. However, there's always those pathological functions that can cause trouble for any of these methods. When selecting a method for solving a given nonlinear problem, you have a number of issues that you want to consider. One, what do you know about the behavior of the function? Where does it cross? And an interval AB satisfying f of a times f of b is less than 0, so opposite signs. First derivative of the function, good initial guesses to the desired root, and so on and so on. There are quite a few things that you need to know for each one of these. In an effort to find the best algorithm for finding a zero of given functions, there are a lot of hybrid methods that have been developed. Some of these procedures combine bisection, used during the early iterations, with the secant or Newton method used to converge quickly in later iterations. There are also adaptive schemes used for monitoring iterations and carrying out stopping rules. Another approach to finding roots is the fixed point iteration. Basically, here we're working with nonlinear equation f of x is equal to 0. We want to know where it crosses the x-axis, just like we were doing with our bisection, Newton, and secant method. What we can do is we can recast this problem as a fixed point problem, x is equal to g of x, for a related nonlinear function g. And then for the fixed point problem, we seek a point where the curve g intersects the diagonal line y is equal to x. And then the value of x such that x is g of x is a fixed point, because we're not changing x when g is applied to it. So there are quite a few iterative algorithms for solving the nonlinear equation f of x is equal to 0 based on a fixed point iterative method. Now, notice they have x to the n plus 1, this is actually a recurrence relation, not a power, is equal to g of the nth recurrence relation of x, where g has fixed points that are solutions of f of x is equal to 0. Initial starting value x is 0 is selected, and the iterative method is replied repeatedly until it converges sufficiently well. Let's take a look at an example to clarify things. So we want to apply the fixed point procedure where g of x is 1 plus 2 over x. Starting with x0 is equal to 1, and compute as 0 the nonlinear function f of x is equal to x squared minus x minus 2. So the fixed point method is x of n plus 1 is equal to 1 plus 2 over xn, with x0 is equal to 1. That's given by our g of x. So x1, that's pretty easy. 1 plus 2 over xn, which is x0. So 1 plus 2 over 1 is 3. x2 is 1 plus 2 over x1, which is 3, and that gives us 5/3. And eventually x8 is going to arrive at 1.994, as you can see on page 148 of the text. Let's take a look at how it's doing that. And in this figure, we can see the steps spiral into the fixed point 2. It should be noted that some fixed point problems are better than others. In particular, g of x needs to be locally convergent for this to work well. By locally convergent, we mean that there's some interval containing x0 such that the fixed point method converges for any starting value x0 within that interval. So this is just another way to solve for roots of equations. Next time we're going to take a look at Chapter 4, and in particular the problem of interpolation.